Hello and welcome to IITian Academy, where we explore the core concepts and big ideas behind physics and mathematics. Today marks the start of our physics journey, and what's a better way to begin than with a topic that forms the foundation of all measurement, calculation, and scientific thinking? Yes, units, measurements, and dimensions. Over the next few lessons, I hope to give you all a better understanding as to how such a seemingly trivial topic, oftentimes taught in a boring manner without much grandeur, is in fact such a strong pillar in physics. Together we shall take on the reins from the very basics to the more mind-bending questions. For instance, can we derive all of the Planck's units through a mere understanding of dimensions? Or in fact, would it be possible to estimate the radius of the blast during the Trinity test using dimensional analysis with only a mere bunch of photographs which were published in a magazine being available? But before we dive into SI units, significant figures, or dimensional analysis, we need to ask something deeper in order to better understand what we are going to study, and not just that, more so as to understand why we are even going to need this later on. And that starts with asking the question, what exactly is physics? So physics is one of the most fundamental sciences. It's the science that studies the nature of the universe, not just what it is made up of, but how and why it behaves the way it does. The ideas of physics are used everywhere, in chemistry, biology, astronomy, or even in geology and medicine. A chemist or a biophysicist might study how molecules interact. A climatologist uses physics to model the atmosphere. An engineer uses physics to build, say, electronic devices, spacecrafts, and so on. But at its core, physics is more than formulae. It's a process, a way of reasoning, of thinking, and a way of understanding. It asks, what rules govern natural behavior? Can we describe them in a general, quantitative way? Can we test them through a series of experiments and through observation? And that's where physics begins, as an experimental science. In physics, we don't just guess. We observe, measure, we form hypotheses, and then we test them. And when a pattern holds, it becomes a principle. When it fails, it's discarded and we move on to a new hypothesis. No equation is treated as sacred. And in fact, that's what makes physics so beautiful and interesting. Every theory, be it Newton's gravity or Einstein's relativity itself, is open to questioning and to refinement. At its best, physics could be thought of as a self-correcting dialogue with nature itself. Okay, so now I believe is a good time to talk about something that needs to be addressed before we make a full-fledged dive into the topic. And this is in regards to a challenge every student faces at some point of their physics curriculum. And what we're talking about is solving problems in physics. It can truly seem frustrating when it happens, when one goes, okay, so I understood the concept, but I just can't solve the problem. Why is that? Well, that's because in physics, understanding a principle is only the beginning. The real test lies in applying it, often in unfamiliar or abstract contexts. That's why problem solving in physics is so crucial. It's a core skill and also a way of learning itself. So a strategy that one might find helpful would be to first identify the concepts and the quantities involved. Then one should frame your equations using those quantities, and then you do the math step by step, and once you have executed it, you finally evaluate, so you reflect if your answer makes sense. Of course, we shall be solving various problems throughout our journey here at IITian Academy, and we shall see how to adopt the above methods effectively to sharpen our problem-solving skills. In due time, you will realize that students of physics don't just memorize equations. In fact, I'd strongly discourage you from doing so unnecessarily, especially without a proper grasp or understanding. What you should learn to do is know how to read a problem, simplify a situation, and ask the right questions. And the first tool that helps one to do that is the idealized model. In real life, objects are complicated. A baseball isn't just a ball, it has stitches, texture, drag, and spin. But when we study motion in physics, we often start by treating this baseball as a point object. And why is that, you may ask? Well, because physics isn't about replicating every detail of the real world. It's about identifying the essentials, the dominant effects, and building a model that we can actually work with. Hence, we make various assumptions. We assume that objects are rigid, surfaces are smooth and frictionless, or that air resistance is negligible, that planets are point masses. And all of these are intentional simplifications. An idealized model lets us strip away distractions and focus on core principles. Later, as we gain tools, we can reintroduce complexity such as friction, viscosity, or chaos. But we must start first with clarity. Now, here's the part where all of this connects to our topic at hand. If physics is the science of measurement and prediction, then we must ask, how do we measure and what do we measure with? And that is where units come in. A number without a unit is just a number. So if you have a question which asks you to find, say, some distance or a time interval or mass, and you obtain the correct numeric value, which for the sake of an example, let's say is 5, but you leave out the units, your answer tends to lack information or meaning. Your teacher might ask you, 5 what? Apples? Bananas? But 5 meters is meaningful. 5 seconds is meaningful. 5 kilograms? Also meaningful. And now we know what we are talking about. More importantly, units give structure to physical laws. Let me give you an example. Suppose someone claims that kinetic energy is m times v instead of half mv squared. Before even checking through an experiment, we can ask, does the dimension match? Energy has the dimension ml squared t to the minus 2, but mv has the dimension ml t to the minus 1, and that's momentum, not energy. So the equation fails, not because of numbers, but because the units just don't work. And of course we shall look into all of these when we go into dimensional analysis. But for now, I hope you just get the idea. And yes, this isn't just academic. So in 1999, NASA launched the Mars Climate Orbiter, a project which was worth more than $300 million. And this was because one team used imperial units, that is the FPS system, for their calculations, while the spacecraft control software used SI units. And the software mismatch caused incorrect thruster firings, hence causing the orbiter to burn up in Mars's atmosphere as it entered the planet's orbit. A simple mistake in units resulted in a total mission loss. So I hope you understand that when we say that units matter, we mean it. So in this video so far, we have seen why physics is a process, not just a body of knowledge, how problem solving is both the method and the outcome, why simplification through idealized models is essential, and finally, why units are the scaffolding of everything we find in physics. In the next video, we'll begin our exploration of physical quantities, the 7 base SI units, supplementary units like solid angles, and how all other physical quantities can be derived from these. So, subscribe to IITian Academy if you are ready to start building your physics from the ground up, one dimension at a time. See you in the next lesson.